All right, as promised, we're going to now prove that this new ring we've defined, S adjoin A, is a subring of R, is a ring in its own right. And as we were doing this, there's one mistake I made in what I wrote down. So we knew that S adjoin A is a subset of R, and we were going to use the subring test. So that means we must show S adjoin A is closed under addition, multiplication, contains additive inverses, that 1 is in there. So we're going to do maybe the easy parts first. And again, this is supposed to be 1 is in S adjoin A. So let's talk about that first. 1 is in S adjoin A because 1 is something that is written in the format of S adjoin A. So remember, S adjoin A was those polynomial expressions in A with coefficients in S. So 1 equals 1 plus 0 A's and 0 A's squareds, dot, 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 dot. So 1 is in S adjoin A because it can be written in that form. Okay, how about additive inverses? So if S0 plus S1A dot 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 up to Sn a to the n is in S adjoin A, then negative S0 minus S1A minus dot 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 minus Sn a to the n is also in S adjoin A as negative S0, negative S1 dot 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 up to negative Sn are still in S. So S was a subring. That means if all those coefficients were in S, then the negatives of those coefficients are also in S. And so that means that the negative polynomial expression is in S adjoin A. Okay, so S adjoin A contains additive inverses. Okay, next, closed under addition and closed under multiplication. So we're going to use that same S0 plus S1A all the way up to Sn a to the n is in S adjoin A. And let's make a new polynomial expression, T0, T1A, dot, 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 up to Tm a to the n. If that is in S adjoin A. And now I'm going to put one stipulation on this. So now what I'm doing is taking any two elements I want from my subset S adjoin A. So these are any two polynomial expressions. In order to do the adding of this, I want to know which one has more terms. So I'm going to say m is greater than or equal to n. And I do that just for convenience sake. So I'm going to take those two things and I'm going to add them together, and I want to know when I add the final term which one is the higher power, right? So I'm going to take S0 plus S1A all the way up to Sn a to the n and add on the T0, T1A, dot, 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 up to Tm a to the m. And when I do that, my sum, I'm going to combine like terms, the way we're used to. So my sum is going to be S0 plus T0 as the leading term, as the constant term there. That's what we usually call it. And then S1 plus T1 is going to be a to the first. That's the coefficient in front of a to the first. I'll write down the second one even though we didn't write it down, just so we see the pattern. So the a squared terms will look like that. And then here came in handy that I said which one was bigger. So we have an Sn plus Tn a to the n, but then the t's might keep going. So there might be a next a to the n plus 1 that only has a tn in front of it because the s's have now run out. And then the very last term will be that highest power of a, that tm a to the m. Okay. All right. And now this is the sum. So why is the sum in S adjoin A? That's the question we want to answer. And the answer is each of these sums of the coefficients is just a sum of elements in S, and so in S. So this sum is in S adjoin A. Okay, so the idea is we took any two elements of S adjoin A, that was this S0 series and the T0 series like that. We added them together and we saw that, look, the coefficients are still in S, and so our sum is in S adjoin A. And now we want to do the same thing with the product. The product, write it down, gets a little messier, but it's not too bad. So I'm going to take those same two elements, so the whole set of S's times, this time, the T expression. Okay, and now I want to multiply these out and see if I still am in S adjoin A, see if I still can be written in that format. So as we do this, it's going to get a little bit messy, but we can do term by term. So if I look at the constant terms, the ones with a to the 0, I'm going to get an S0, T0. If I look, where do I get an a to the first power? I'm going to get that from S0, T1 and from S1, T0. Okay. If I can do this without even writing it down, I can think through where would I get a squareds from. I would get a squareds from an S0 term times a T2 a squared. And I would get more from the S1 T1, and I didn't leave myself quite enough room. I would get another a squared, so that was from the S1a T1a, and I would get another a squared from the S2 a squared times T0. All right, so my a squared term will end up looking like that, and this continues. They get messier and messier as you go along. They get to be longer and longer expressions all the way till the end, where you have an Sn Tm, a to the n times a to the m gives me an a to the n plus m. Okay, so that's my whole product, and I skipped over the messy parts, but that's okay. The important part here is that all those coefficients are sums and products of elements from S, right? All the S's and all the T's were in S, and so any sum or product of those things are going to be in S. Okay, so thus this product is in S adjoin A. And that's the end of our proof. We showed that S adjoin A is closed under addition and multiplication. That's these last two we did. We showed that 1 is in there, and we showed that additive inverses are in there. So that means it's a ring because it's a subring of R. All right, so that's the proof that this set that we came up with, let me go back up to the top to see it, all these polynomial expressions, coefficients in S, this is a new way to form a ring, and it's a subring of R. So we're going to see this a lot. In the next video, we'll work through some examples of what more of these things actually look like.